Okay, now we're going to do section 2 of chapter 4, structure of the nuclear atom. Okay, here we have a picture of an X-ray of someone's hand. So we can't see what your bones look like by just looking at your hand. We can kind of see some things. Maybe if you have a broken bone, we might see something's not right. But we can really see where your joints are connected by using an X-ray. So there's lots of methods that we can use to see inside the atom. And that's what this section is about. Okay, we're going to talk about 3 main kinds of subatomic particles. Okay, so we're going to talk about 3 kinds. There's electrons, protons, and neutrons. So electrons have negative charges, protons have positive charges, and neutrons are neutral, no charge. So we often write it with a plus and a minus like that. And we're going to talk about how these things were actually found. Okay? Okay, so when we start talking about these subatomic particles, this gives us a problem with Dalton's atomic theory because much of it is accepted, but there are some changes. Because now, look at this, didn't I tell you, remember the word indivisible? We know that atoms are divisible because they can be broken down into what we call fundamental particles called subatomic particles. Now the thing with this is a fundamental particle is not unique like an element is unique. So an atom is going to be a unique element. An electron or a proton or a neutron is not. It could be from any element. Okay, that's going to be what our difference is. So the next person after Dalton comes along in the late 1800s, early 1900s, a gentleman named J.J. Thomson. He was from England also, and he was an English physicist. And he came up with the concept that electrons were negatively charged, as I had shown you. Okay? Now, how did he come up with this idea? Experimentation. If you said experimentation, that is great. Okay? So he experimented by passing an electric current through gases at very low pressures. So he had the gases in a glass tube, and at the ends he had metal discs, which he called, you got it, electrodes. We all know about electrodes today. And the electrodes were connected to electricity. Okay? So if you think about this, when was electricity discovered? When were people doing things with electricity where they could actually contain it? That's the time frame. All right, so here's a picture of his device. This is called a cathode ray tube. Okay? And here's our gas at very low pressure. Here's a source of electricity. Looks like a battery, right? 2 metal discs. One's called the cathode, one's called the anode. And it's under vacuum. That's keeping it at low pressure. Okay? And so he observes these rays that are going from one disc through the other, through the gas, and they'll have a color due to the type of gas that's in there. So he can see these cathode rays. They're called cathode rays. Okay, so that pretty much sums up this cathode ray tube. So this is the device he used to see what happens. And he found some interesting things of it. Okay, so normally, here we go, we just have a nice straight cathode ray going from one spot to the other, from the cathode to the anode. Now, when he took some magnets or electrically charged plates Okay, so this one's negative, this one's positive. He notices that the cathode ray is deflected. Now look at what he's done. He's taken that big cathode ray and put it through a slit. Again, a typical physics experiment where you take light and put it through a small slit. So now he has a small stream of light, and these rays are attracted to the positive plate and repelled from the negative plate. So what can you say about these rays? Okay, so if it's attracted to positive and repelled from negative, then the rays themselves must be negative. So he knew that opposite charges attract one another and light charges repel. So he made a hypothesis. He said the cathode ray is a stream of teeny, negatively charged particles, and they move very quickly. He called these corpuscles. Where do you think he got that term from? Biology. Okay? It was later that we came up with the term electrons. All right, here's a real picture of the cathode ray in action. And as I said, there's a magnet. You don't really need to have two different plates. A magnet will work the same way. So now he wanted to test this hypothesis. So he wanted to measure the ratio of the charge and mass of this so-called electron. And he found that this ratio is constant. He also did something, and he found that the charge to mass ratio of electrons do not depend on the kind of gas or the type of metal used for the electrodes. So that tells you that it's not specific to a certain element, that these charges were independent particles that were not unique to specific elements, which said they were smaller than atoms, because the smallest particle we had right now is unique. Okay, so this is a big, big change. So from this, he was able to conclude that electrons are a component of the atoms of all elements. So it's a particle that makes up every element, but it's not unique to a given element. Okay, another person was working around the same time called Robert Millikan, and he wanted to find what was the quantity. So he's looking for a number of an electron's charge. He did something called the oil drop experiment, Millikan's oil drop experiment. So he took negatively charged oil droplets and he suspended them. He made them float basically between two charged plates. He then changed the voltage on the plates to see what happened to the droplets. Did it stop them from falling? Did it make them fall faster? That's what he wanted to know. And from this experiment, he found that the charge on each oil droplet was 1.6 times 10 to the minus 19 coulomb, which is a measure of charge. So he said this was the charge of an electron. Okay, and from this information, using Thomson's calculation on the charge to mass ratio of an electron, Millikan could then calculate an electron's mass. And it's very, very close to what we use today. So an electron has 1 unit of negative charge and its mass is 1, oops, keep on pressing the button. It's 1/18 over 40 the mass of a hydrogen atom. So a hydrogen atom is the smallest atom. So this is that almost insignificant number. Very, very small mass. So if cathode rays are electrons given off by atoms, what remains in the atom? So if we took an electron away from hydrogen, what's left? Well, we know that all atoms are neutral. So if we take away a negative charge, there must have been a positive charge there. So there had to be something inside the atom that was positively charged. Okay, so we know that there's no net electric charge. They're electrically neutral. Electrical charges are carried by particles of matter, and electrical charges always exist in whole number multiples of a single basic unit. There's no fraction of a charge. So when a given number of negatively charged particles combines with an equal number of positively charged particles, a neutral particle is formed. So therefore, there must be something positively charged. So if we took one electron away with one negative charge, 1 unit of positive charge must remain. So that would be what would happen to a hydrogen atom. It has 1 positive and 1 negative charge. So when it's by itself, it's neutral. And then if you took the electron away, it would have a positive charge. A man named Eugen Goldstein observed a cathode ray tube and found rays traveling in the direction opposite to that of the cathode rays. So what did he discover? He said they must be positive particles, and he called these protons. Okay? And then Chadwick comes along in 1932, and he's given the idea of another subatomic particle that does not have a charge at all, but adds to the mass of the atom, and he called that the neutron. So here's a table that gives you some information about these 3 subatomic particles. We have electrons, protons, and neutrons. Their symbols: electrons are an E with a little negative sign, protons are a P with a positive sign, and sometimes you'll see a proton written this way. Sometimes you'll see it as H for hydrogen plus, because a hydrogen atom stripped of its electron is a proton. And then a neutron is N with 0, telling us it has no charge. Okay, so here's our charges: -1, +1, and 0. Our masses, these two are equal, so we're going to give them a value of 1, and this is 1 over 1840. That makes our math easier because the actual mass in grams, even the protons and the neutrons, are very, very small. Okay, but it's 10 times 10 times 10 times 10 times smaller almost for an electron compared to a proton. Now, we're not going to get into this other than mentioning it here, is physicists even think that protons, neutrons, and electrons are very, very small. But there's even something even smaller that's called a quark, and quarks make up the subatomic particles. Okay? That's beyond chemistry. That's physics. Okay, so let's think about what we learned. What evidence did Thomson have to led him to conclude the cathode ray was a stream of teeny negative charged particles? Describe his experiment. The ray was attracted to a metal plate with positive electric charge, and Thomson knew that opposite charges attract and like charges repel. Now, let's talk about the nucleus. These electrons were out and gone. So something has to be inside the atom. So we call that the nucleus. Okay. First, Thomson proposed there was something called the plum pudding model, okay? Meaning that if I draw, I like to think of this as the, not the plum pudding model, because plum pudding is something, if you're English, you might know what plum pudding is. We eat chocolate chip cookies, so I like the chocolate chip cookie model. And the chocolate chip cookie model is if you draw chocolate chips, you'll see chocolate chips all over the place. Now, just to let you know what a plum pudding is, this is like a cross-section of a plum pudding. A plum pudding is a sphere with lots of raisins in it. So J.J. Thomson thought that the model of the atom would be a sphere, and the raisins would be positively and negatively charged particles spread out throughout the whole round sphere. If we take this cross-section with chocolate chips, some of the chocolate chips would be negative and some would be positive, uniformly distributed, so there's a net charge of 0. Okay, so that's basically Thomson's idea. Well, one of his students came along named Ernest Rutherford. He was born in New Zealand, way over in the South Pacific. Okay, and he got a Nobel Prize in Chemistry in 1908 for his work. He also appears on the New Zealand $100 bill. So he did something called the gold foil experiment. And he was really trying to test the existence of the plum pudding model, but he found something else out. He used alpha particles, which are helium's nucleus. Okay, they lost 2 electrons. Okay, he didn't know that this was the case at the time. They knew about alpha particles. And it has a double positive charge because of the 2 remaining protons. So he's going to use these alpha particles as bullets. And he's going to shoot them through a piece of gold foil. And he's going to have a screen that will have a fluorescent spark, more or less, when the alpha particles hit the screen. So at this point, one of the things that people were saying is, since these electrons and protons have to be separated a lot, it was and they were evenly separated, then some of the gold foil, some of the particles should be deflected if they go near a proton, and they should be attracted or deflected towards an electron. But most of the atom is going to be empty space, okay, between these particles. So he saw a lot of that, but he was really perplexed, because if we look at this picture, okay, doesn't want to give me my... Anyway, so if we look at this, there we go. If we look at this picture, look at over here. How did these get back here? Well, if you play pool, if you hit something, something goes back that way. So somehow, these couple of things must have hit something. All right? We expected them all to go through with a little bit of deflection, not to do this. So what caused that? So his idea was they were all going to go straight through. But occasionally we would see some ricochet back. So what in this model, we're seeing that it's hitting some mass and hitting it back. Okay? So from this information, it's saying it must hit something like a pool ball. Right? So that's where we get the idea of the nucleus. Okay, so answering the question at the beginning of the slideshow. Okay, how do you see inside the atom? It's how it interacted with particles with known properties. So how the atom interacted. Like the negatively charged electrons in the cathode ray experiment or the positively charged alpha particles, how did it behave? So what we were able to do is he said the atom was mostly empty space, okay? And somewhere in this atom, okay, and that's why the lack of deflection of most of the alpha particles, they went right through. Okay, that's what they thought. However, the ones that bounced back were very few, about 1 in every 8,000 back, flipped back. So that says that if you're setting positive charges, it must hit something and also be repelled by it very, very strongly because it's concentrated, and it must be where the mass is located. So therefore, there must be a center of mass. And so this is where he gets the idea that the positive charge is in the mass, is in the center of the atom. Okay, so that's where we come up with the idea that the mass is located in a positively charged nucleus, and we now know protons and neutrons make that up. The electrons then are outside the nucleus, and they are occupying this empty area except for the little teeny point negative charges that are very, very small compared to the nucleus. All right, so if you want to look at something to compare it to, if you think of the atom the size of a football stadium and the nucleus the size of the marble at the 50-yard line, that gives you an idea of how small the nucleus is. So sending these helium alpha particles is like sending it through a football stadium and it hitting the marble in the middle of the football stadium. Now, later on, this model has been revised too to also explain some of the chemical properties of the elements. But this lasted for quite some time, and it's kind of the model we tend to use when we think of the atom in general, but we're going to find much more specific models that use mathematics to describe things about the atom. Okay, what evidence from Rutherford's gold foil experiment disproves J.J. Thomson? J.J. Thomson was not too happy that his student found this out. Okay, but basically because most of the particles passed through without deflection, meaning they weren't deflected by positively charged chocolate chips. Okay, and a small fraction were deflected at large angles, signifying they hit something very massive, and it was located in a small amount of volume of the atom itself. If the Plum model was true, then they should have been deflected at small angles, evenly spaced, from either interacting with electrons or positively charged species in the chocolate chip cookie. Okay, in summary, we talked about the 3 types of subatomic particles: the ones that are located in the nucleus, the ones that are located outside the nucleus. There's your definitions that you need to write down. Turn off the video to write those down. And your big idea for this section: atoms have positively charged protons and neutral neutrons inside a nucleus and negatively charged electrons outside the nucleus. And that's it for